Welcome to the 12th lecture of the course Turbulence. So, let us start with the turbulent energy equation which we started discussing in the last class. So, it was U j P u j bar minus rho plus twice nu bar u j bar, this is the transport term, and then we have another two term. One is our dissipation term, that is twice nu small s I j bar, this is our dissipation term, and the last one is our production term, that is this, right. So, in the last class we discussed mainly the discussion was based on homogeneous pure shear flow, where except u I all average quantities with respect to space are 0, right. So, and this was our dissipation. We said that the dissipation occurred at very small scales, where the viscosity can work on the eddies and can smear out these eddies from the turbulent flows, and whereas your production occurs at the larger scales. Okay. So, that is what we have talked about. So, we will start with this discussion once again, because we are not yet done with this discussion. Okay. So, if we consider considering once again homogeneous pure shear flow, okay, we can say this left hand side is 0, as well as this transport term is also 0 for this, and for that particular case we can get this minus u I u j bar s I j is equal to your dissipation, which is small twice nu small s I j bar, right. So, that is what our argument, okay. And then what we did, actually we considered that the scale velocity turbulent velocity scale to be u t. Okay. So, we can define that u t, okay, which was not defined in the last class. So, we can define u t as 1/3 of u I bar. Okay. So, so 1/3 of u I bar, and if I consider this, then what do we get? So, this is essentially your u1 square bar, u2 square bar, u3 square. So, you can consider this is what is your ut. So, that based on that, if the flow is homogeneous and isotropic, so in that particular case, so isotropic means I said that u1 square bar is equal to u2 square bar equals to u3 square bar. So, in that particular case you see what we get here. So, in that particular case what we get 3 into u1 square, right. So, essentially this half should be then this should be outside, sorry, this 1/3 if I take outside, then what it is happening. So, this is u1 square plus u3 square plus u1 square plus u2 square plus u3 square divided by 3. So, in the case of isotropic turbulence all 3 are equal. So, basically so this is this should be this should be half. Okay. So, this is what the ut scale can be defined. So, by definition turbulent velocity scale can be considered as this, and for isotropic turbulence case, then this equals to actually your nothing but your ut square. Okay. So, that is what it says. Okay. So, from that particular argument, then you see this term we designated as production, and this term we designated as dissipation, if you can remember. So, our production term, if we consider from this argument our production, so P can be written as, if we use equal sign instead of order of magnitude, then one constant will come here. So, let us say that constant is C1 into the order of this particular term. If we can consider the order of this term, which is nothing but we can write this as ut square, and this is what is your capital Sij. Okay. So, what we can do now, this particular this particular term in the last class, how we modified, if you can remember that we wrote that P is equal to C1. So, that ut square we can write as ut, and 1 L UL and ut this L, let me take it here, and Sij. Okay. So, this I can write as C1 ut L, and this one once again of the order of Sij. So, so basically before considering the C1, so let me just consider C1 little later. Okay. I am sorry. So, this can be written as of the order of this. Okay. And this then can be written as order of this, right, which can be written as C1 if I equate that production is equal to some constant C1 into ut into L, and this I can write as Sij Sij. Okay. So, this is what is our production term, and our dissipation term is once again is this. Okay. So, this is what is our dissipation term. So, now production balance, when production will balance with dissipation, we can write from this. So, so for production balancing dissipation, we get what? We get C1 some constant ut L capital Sij is equal to our twice nu small Sij bar. Okay. So, you see if I take this nu in this side, so that means C1 REL, okay, C1 REL Sij twice. Okay. So, from these for very large Reynolds number, from this relation, what do we get? From this relation we can find that this from this relation implies that for very high Reynolds number Sij bar is much greater than capital Sij for large REL. Okay. So, here I have not mentioned what is L. So, please note that L is turbulence length scale. Okay. And your ut is turbulent velocity scale. Okay. So, these are characteristics length and characteristics velocity scale of turbulence. So, characteristic length means it can be integral length scale, which we have already defined. Okay. So, that this particular L is defined as the characteristic turbulent length scale, which is nothing but your integral length scale, okay, or measure of the maximum length scale in a turbulent flow can be considered as the integral length scale, which we have already defined. Okay. And ut is also defined here in this particular expression. Okay. So, with this scale we get this particular equation. So, for very high Reynolds number, this is what is our relation. Now, see Sij, the small Sij and capital Sij. So, these are what? These basically unit of time inverse. Okay. So, basically this particular, so Sij is second inverse, right. So, that means from this particular relation what do we get? See, Sij means 1 by second, this capital Sij 1 by second. So, this is time scale. So, this is related with a time scale, this is also related with some time scale. So, it is this particular relation says the time scale of small Sij means time scale of fluctuating strain rate tensor should be much smaller as compared to the mean flow time scale. Okay. So, the time scale from this relation we can say the time scale of small scale fluctuation is much smaller as compared to the mean flow time scale. Okay. So, there one important point is there. What is that? So, that is what we have to figure it out. Okay. So, the time scale, what it says from this relation, it says the time scale, that small time scale or the dissipation time scale is let us say it's tau. So, this is much smaller than the mean flow time scale, let us say it's capital T. Okay. That is what it says. Okay. So, if this is the case, then one important conclusion also comes out from this particular balance. So, that is what was missed in the last class, and let me discuss here. So, what is that? Okay. So, basically what do we say here? You see that small scale turbulence and the large scale, which is of the order of large time scale, which is of the order of your maybe the mean flow time scale, are not tuned in the sense their frequency, their frequency is way apart. So, large scale frequency, the frequency of the small scale at scales where the turbulent dissipation occurs are different. Okay. So, that means they are not correlated. Okay. So, that means the scale at which the turbulent dissipation occurs and that scale at which your that energy extraction happens from the mean flow, they are not kind of correlated. If they are not correlated, then what happens? The small scales have their sort of own life, means the large turbulent scale which are essential for extracting energy from the mean flow is kind of not disturbing the small time scale or the small scale turbulence at which the dissipation is occurring. Okay. That is what we can conclude from this. Why? Because you see, correlation we have already discussed about correlation. So, if you see, let us say the large scale turbulence, okay, which is having this kind of, let us say the large scale turbulence at which that let us say your energy extraction is going on from the mean flow, they are sort of time series, let us say something like this. Okay. And suppose we have another time series signal of the similar shape. Okay. Let us say this is signal time series signal 1, this is time series signal 2, and the correlation between 1 and 2 is going to be high. Why? Because if you see their frequency almost same. Okay. So, if this is time, if you see their frequency is matching, since their frequency is similar, they will highly correlate, because why? So, let us say this is your some signal, this is let us say some signal q1, this some signal q2. So, q1 and q2 their correlation is always high. Why? Because their frequency similar. Why? Because you see when you take this point, the corresponding point is here. So, their multiplication is always high or positive. Similarly, you take this point, multiplication is positive. Take this point, their multiplication is positive. Similarly, this one positive, this one positive. Whereas, if I consider this and some other scale which is very fine scale, if I consider, let us say this is very fine scale, I have very fine scale some q3, okay. Let us say this is q3 and I am trying to correlate this, let us say the q1 and q3. So, q1 and q3, this correlation will not be significant. Why? You see, for example, I would like to take this point down, okay, somewhere here, okay. Then somewhere here, if I take this point down, it is somewhere here, okay. So, like that you see this point, if I take it, it is somewhere here, this point I take it 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 somewhere here. So, this point I take it somewhere here, okay. So, like that is going on. So, what it is happening, you see, for this first two case q1 and q2, if I multiply data at this point and data at the corresponding point in the time series 1, then we always get positive. Similarly, at all other points, whereas in this particular case this is not the case. First, its amplitude is less, second, its frequency is much higher compared to this compared to the frequency here, and we are plotting in the same time scale, let us say, okay. So, frequency means one time period. For this particular wave, the frequency is here to, I mean the time period is this much, and for this case time period is, let us say, from here to here, okay. So, what is this? So, that means this time period and this time period is much smaller as compared to these. So, frequency of this is much smaller compared to the frequency of this. So, their frequency is not tuned, their frequency is way apart, that is what these two series says. And once their frequency is way apart, then what is going to happen? You see, if you take this point, the corresponding point is 0 here. So, their multiplication is going to give you 0. Next point, which is maximum in this case, and the next point is somewhere again is near to 0. So, again this multiplication q1 and q3 is going to be 0 for this case as well. Similarly, if you take other point, there will be many such zeros or low values of this correlation coefficient, okay, in the average. So, which is not the case in this first, okay. So, as a result, what is going to happen? This value is going to be very small as compared to the value q1 q2, okay. So, that means what we can say, these two signal highly correlated, whereas this high frequency and this low frequency, they are not well correlated. That means what? The small scale turbulence at which the turbulence dissipation is occurring, their frequency is very high, okay, because their time scale is much smaller as compared to the time scale of the large scales at which the energy extraction is going on from the main flow. So, this particular small scale turbulence is not highly correlated with this large scale turbulence. So, we can say the small scale turbulence as if they are independent of the large scale turbulence, they are not influenced by the large scale turbulence due to this reason, okay. They are not influence. So, they are sort of independent of the large scale turbulence. Since they are independent of the large scale turbulence, they tend to be isotropic, means their orientation does not matter. Okay. So, their statistics does not depend on the orientation or rotation of the coordinate systems. Okay. So, they are sort of isotropic, or they tend to be isotropic. That means, the small scales at which the dissipation occurs, they tend to be isotropic. Okay. Whereas, the biggest eddies or the largest eddies are always anisotropic, because their orientation is their orientation depends on the mean flow shear. Okay. So, that is why they are sort of anisotropic, and this particular small scale is sort of isotropic, and they are kind of independent of this particular large scale structures at which the energy extraction is going on. Okay. Another point, interesting point to note here, if you see this particular equation and see this, okay, if you see this, larger the scale, larger the turbulent flow scale, higher the production, because it is sort of proportional, right. So, this L, that means if your flow domain is very large, so in that case the turbulence scale also can be very large. So, in that particular case energy extraction from the mean flow will be large. Okay. That is what this particular expression says. Okay. So, from this particular exercise, what we understand, we understand that the small scales are kind of independent of the large scale, or the small scale of turbulence are sort of or tend to be isotropic. Okay. All right. So, now this is what about the this particular production term. Now, let us consider this particular dissipation term. Okay. This is what is your dissipation term or epsilon term, that is what we have considered. So, we have considered in the last class, if you consider that epsilon as your twice nu small Sij bar. Okay. So, this particular expression for isotropic and homogeneous and isotropic turbulence, this particular expression can be written as, so let me just write this. So, this is nothing but your del ui del xj plus del uj del xi. Similarly, del ui del xj del uj del xi. Okay. So, this is what is your expression. So, if you multiply, so this particular term for if you consider the flow is isotropic and homogeneous, then eventually you will be able to show this as 15 nu this del u1 del x1 square bar. That is what it will come for isotropic turbulence. Okay. Isotropic means, as I said, that u1 square is equal to u2 square, sorry, u1 square. Isotropic means I have mentioned that it does not depend on the orientation of the coordinate axis. So, in that particular case, u1 square is equal to u2 square equals to u3 square, right. So, this is what is isotropic, and all other diagonal component of the Reynolds stress tensor are 0. Okay. So, that is what the turbulence we are considering, and for that particular case your dissipation is equal to this. Okay. Now, comparatively measurement of this particular quantity is easier. Okay. So, that can be done. So, now before we proceed, what we can do here, if we consider, okay, if you consider this, if we define this particular quantity, by definition, if we consider this u1 square bar, okay, and lambda g square. Okay. So, what we are trying to consider here, see, we are trying to estimate this particular quantity using u1 square bar, which is nothing but u RMS square, okay, divided by some scale, square. So, by definition we can consider, if we consider that, if we consider this particular definition, then our this epsilon expression, then epsilon becomes what? 15 nu u 1 square bar lambda g square. Okay. What is this? We have to understand here, or since the turbulence is isotropic, this equals to your u t square. Okay. So, which is nothing but your 15 nu u t square by lambda g square. Here the lambda g is Taylor microscale, okay. It is known as transverse Taylor microscale. Okay. So, our idea is that we are trying to estimate the value of this particular term considering the velocity scale equivalent to the turbulent velocity scale. If we consider a turbulent velocity scale here, then to get an estimate of epsilon for the isotropic turbulent case, we have to use another length scale here, which will give you the estimate of this quantity. Means in an actual isotropic turbulent flow, if you would like to measure this particular quantity and would like to find out the epsilon value, whatever value it will come, if you use u t square, then you have to use the length scale to get the same value, and that length scale is found to be lambda g square. So, that is known as Taylor microscale. Okay. So, that means we have to understand one thing, that means this particular quantity, as if we equate twice nu small Sij bar to this particular, from this you can also write this equals to, by this is just by your definition for the timing. If you consider your 15 nu u t square by lambda g square, then someone may think that the velocity and the length scale associated with this small fluctuating strain rate tensor is u t and lambda g, but this is not the case. Okay. These are not the velocity scale and length scale associated with the dissipation of turbulence. Okay. So, these are not dissipative turbulence scale, keep it in mind. We are defining this scale in such a fashion so that we can get the same value of epsilon if we consider turbulent velocity scale here. With that, if we use this particular length scale, okay, which is defined by Taylor, or which is known as Taylor transverse Taylor microscale, then this will give you the same value of epsilon. Okay. So, now we will show this particular scale, I mean this value actually is associated, this particular scale is associated with the curvature of the correlation function. That is what we are going to show later. Okay. So, essentially what we are saying, that this particular quantity can be related to this particular value. Okay. Considering a turbulent velocity scale here, we have to use a length scale such that the value equals the value of this equals the value of this actual value of this. Okay. So, that is what it means, keep it in mind. Okay. But once again, u t is not the velocity scale for dissipative eddies, lambda g is not the length scale of the dissipative eddies. Okay. These are only used to get an estimate of the dissipation. Okay. If we use the turbulent velocity scale, then we have to use another scale such that we get the right value of dissipation. and that scale is known as this Taylor microscale. Okay. So, and another there is a relation of Taylor microscale in isotopic turbulence flow. There are two types of Taylor microscale, one is transverse Taylor microscale and longitudinal. Okay. So, another is and which we know as lambda 1. Okay. And the relation between the lambda 1 and relation between lambda 1 and lambda 2 is going to be your lambda 1 square by 2 equals to your lambda 2 square. Okay. Or this is that longitudinal Taylor microscale is designated sometime by lambda f. So, then the lambda f square is equal to lambda g square, okay, whether f and g are denoted as longitudinal and transverse Taylor microscales. Okay. So, that is this is only for the isotopic, this is only for the isotopic turbulence case. Okay. Keep it in mind. Okay. So, so that means this particular relation, if you note, if you consider the transverse Taylor's microscale instead of transverse Taylor microscale, if you use the longitudinal Taylor microscale, then this particular quantity is going to be what? This is going to be lambda f square and this is going to be 30 nu. Okay. Please keep it in mind. Okay. So, what is this that I will just come in a minute. Okay. So, before that, let us just establish some relation, okay, based on this based on the based on the balance of production is equal to dissipation. Okay. So, homogeneous shear flow, pure shear flow, what do we got? P is equal to epsilon, right. So, what is P? P we got minus ui uj bar capital Sij is equal to epsilon, which is equal to twice nu small Sij bar. Now, what we can write now from this particular expression, you see this I can write as what is the order of magnitude of this quantity? ut square. What is the order of magnitude of this? ut by L. So, this particular quantity I can write some constant into ut turbulent velocity scale square, and then I can consider this as ut by L, okay, is equal to our dissipation epsilon, right. That is what I can write, right. So, or you see that A is a constant here. So, ut cube by L equals to epsilon, okay, and epsilon is equal to what? Twice nu Sij, and if it is isotopic turbulence, then we can write this as 15 nu ut square by lambda g square. Okay. Now, from this what we get, you see, from this we can write your lambda g square, and I can take L square here, then I can take this 15 by A, and one nu remains here, and in that particular case L square I have taken. So, one L needs to be taken here into ut. Okay. So, this A has gone here, nu is there, ut. So, ut square cancel out, one ut is there here. So, L is here. So, that means you see what we get, lambda g by L is equal to what? Lambda g by L is nothing but your 15 by A half, and what is this? REL, right, nu by L ut. So, it is a Reynolds number. So, 1 by Reynolds number. So, that is REL power half, right. So, this is what one relation. So, this is what is our one relation. Okay. So, you see another relation we can get from this. Once again the same formula we can write it here, same, this I am starting from here. So, this I can write is as ut square, sorry, ut cube by L equals to 15 nu ut square by lambda g square, right. Or what I can do, one lambda I can take here. So, lambda z by L I keep, and here 15 nu is there, u2 is down and one lambda is here. Okay. So, and a, okay. Or you see lambda z by L, another relation I get which is 15 by a, and this is your Re lambda, okay, Re lambda minus 1. So, there are two relations. Okay. So, this is my relation number 2. Okay. Using these two relation, you can find a relation between Re L and Re lambda. Okay. Using these two relation, you can find your, I mean you can find relation between Re L and Re lambda. Okay. So, this is one exercise. Now, we have to mention another point here which we have not done. So, dissipation occurs at what scales, or how to find out the dissipation length, velocity or time scales. Okay. So, that is what is our next question. Okay. So, you see dissipation other day, if you can remember what we said, that energy extraction from the mean flow by the large eddies is basically in Mischit process. It does not depend on the viscosity. Okay. So, the big eddy due to the straining, due to the strain field of the main flow extract energy from the mean flow, and the eddies which are there, or that particular eddy again will break to smaller eddies and give its energy to the somewhat smaller eddies, and that smaller eddy again even smaller eddies, and so on to the viscosity, right. Now, here the energy which is coming from the mean flow, or which is extracted from the mean flow by the large eddies, are cascaded down to the smaller and smaller and smaller scales, right. And then the scales become so small, so that the viscosity can smear out those very small scale turbulence. Okay. That is what we call it dissipation, right. Now, we ask how to find out then dissipation scale. Okay. Now, to go about these dissipation scales, if we consider the dimensional ground, then we have to first ask the dissipation scale depends on which parameters. Okay. If we ask these questions, then we will figure it out. You see, it depends on two things. One is viscosity, okay, because finally viscosity is smearing them out from the turbulent flow. Okay. So, viscosity is a parameter. What else? Another parameter is that at rate which the energy is received by the small scale. Okay. So, that is the rate of energy, or rate of energy which is cascaded down to the small scale. So, if it is higher, then that dissipation rate will be higher, right. So, that is why these are the two parameters on which this small scale or dissipative eddies depend on. Okay. So, that means there are two parameters here on which the dissipation scales depend. What are those two parameters? The two parameters, one is epsilon and another is your viscosity. So, based on these two parameters, we can find out the dissipative scales. Okay. So, that is what is our basically Kolmogorov scale. Okay. And let us just find this. Okay. So, we said that small scale depends on two parameters, that is epsilon and nu. Okay. What is epsilon? epsilon the rate of dissipation, which is equal to what? The rate of dissipation, production is equal to dissipation. Okay. So, that means this epsilon is actually at what rate that energy is produced, at the same rate it has to dissipate. So, it depends on this dissipation and it also depends on the viscosity, right. So, if this is the case, then based on these two parameter we can define a length scale, okay. And this is from the dimensional analysis, if you figure it out what should be the length scale, that is nothing but your nu cube by epsilon to the power 1 by 4. This is what is your length scale. So, this is what is your Kolmogorov length scale. Okay. So, this is what is our Kolmogorov length scale. Similarly, we can define a velocity scale, and Kolmogorov velocity scale V k, if we call it, then that is du by epsilon, sorry, Kolmogorov time scale. Okay. So, Kolmogorov time scale, let us call it tau eta, which is nothing but your this, sorry, 2 it should be. Okay. So, this is Kolmogorov time scale, okay. And length scale you have got, time scale you have got. So, length divided by time scale is nothing but your velocity scale. So, if you find out the Kolmogorov velocity scale V eta, so that is going to come as nu into epsilon to the power 1 by 4. I am not sure, let us do it. Okay. So, this is your Kolmogorov velocity scale. Okay. So, this is what, this one is meter square per second and this one your u cube by L, right. So, u cube by L, so that means meter cube. So, meter square, so this meter square per second, meter square per second square, right. So, that means it is going to be meter square per second, this is meter square per second square, this is meter square per, this is meter square per second, and this is meter square per second cube, this one. So, that means you see what is happening, length to the power 4 divided by time to the power 4, which is nothing but your length. I mean, if you take 1 by 4 of this, which is nothing but your length divided by time, which is nothing but your velocity scale. Okay. So, this is correct. So, this is Kolmogorov velocity scale. Okay. So, these are the scale, keep it in mind. So, these are the scales at which turbulent dissipation occurs. Okay. So, that is what the point here. Now, you see that if you would like to find out what is the scale ratio that Taylor microscale, which was just defined some time back, and eta. So, if we figure it out this particular ratio, I mean if we would like to figure out the ratio between Kolmogorov and the Taylor microscale, then we have to work with this particular relation, and if you see that eta equals to, or let us use this particular relation, and let me do it here. Okay. So, equation 2 we have got it here, 1, equation 2, equation 3 we are going to get it from there. So, eta to the power 4 is equal to, can be written nu cube by epsilon, which is nothing but your nu cube by epsilon, which is 15 nu u t square by lambda z square, right. So, that means you see what we are getting from here, this nu square, 15 is here, one nu cancel out, then u t square, okay. Then I can take one lambda g square, then I can write it here lambda g to the power 4, okay. Or I can write eta by 4 eta z 4 equals to what? Equals to my this quantity. So, that is 1 by 15 and this is 1 by R e lambda square, sorry, yeah, square, right. So, that means from this what we can get lambda g y, if I would like to write other way around. So, that means my lambda z by eta, okay, 4 equals to 15 R e lambda square, right. So, from this essentially we get lambda z by eta equals to 15 to the power 1 by 4 R e lambda half, right. That is what we get. So, that means let me write here itself final relation, okay. So, final relation what we get from here, that is nothing but your lambda z eta, the ratio of this is nothing but your 15 this and R e lambda half, okay. This relation 3, okay. So, from this relation 1, relation 2, relation 3, you get the relation between lambda z and integral length scale L, lambda z and integral length scale and relation with R e lambda, or lambda z with eta, means Kolmogorov length scale. Now, I want you to find a length scale or ratio eta versus L, okay. What should be the ratio of this, okay. Take this as an assignment and do this, okay. So, with these scale relations, okay, we are kind of okay. Now, still there are some things to to understand further, that is your, as I have mentioned, the Taylor scale, how this particular relation, as I have mentioned, how this particular relation can be written as this equals your basically 15 nu ut square by lambda g square. So, that is what we are going to work with now. So, before we proceed with this, I would like to mention the correlation tensor, definition of the correlation tensor. So, let us say correlation tensor, definition of that is, let us say Rij. Rij is a function of R only, okay, and this can be defined as, let us say Ui R or T Uj x, okay, and normalize, you need to normalize. So, that is square bar, similarly Uj square bar, okay. So, this is what is our correlation tensor. You can correlate either u with v or u with w or w with u, whatever it is. So, only in that case you have to change the I can be 1, I can be 2, I can be 3, I can be similarly j can be 1, j can be 2, j can be 3. So, for any combination you can find this value, okay. So, we are not going to that much details. So, here we would like to define let us say this R, let us say this, we are going to define this R for I, if we consider this, okay, then we can write is as you see I t, then this also I can write as this and okay, r. So, r you can okay, you keep this as this only for the time being. So, I am just making it simpler. Okay. Instead of this tensor, I am just considering I. So, in that particular case, I can consider here, and here I can consider this bar, okay, ui square bar, right. Now, what I can do, I can even more simplify. What I can say RII, let us say instead of this R I would like to take in the direction of, so this vector x. So, this vector x I can once again denote it as, let us say xi t and xi that r. Okay. So, let us say that r is in the direction of vector xi. Okay. So, this is ui it should be, and ui square bar, this is just normalization or normalizing constant. Okay. Now, you see here what is going on. Let us say that correlation, this particular correlation function, when your ui and r is parallel, then we can call this correlation function as longitudinal correlation. When ui and r are parallel, we call this correlation function as longitudinal correlation, whereas when r and ui are perpendicular, means if it is u1 and r also goes along the x1 direction, then it is longitudinal correlation. Similarly, if it is u2 and r goes in the direction of x2, then also it is longitudinal correlation. Similarly, if it is w or u3, if it is u3 and r goes in the direction of x3, then also it is longitudinal correlation, whereas if it is if it is, let us say u1, but r goes in the direction of x2, then it is transverse correlation. Similarly, if it is u2 and r goes in the direction of x1, then it is transverse correlation. Okay. So, in the case of isotopic turbulence, the longitudinal correlation for for isotopic turbulence, the longitudinal correlation function is denoted by the longitudinal correlation function is denoted by f of r. Okay. So, that means this particular quantity we are going to call f of r when this ui and this r are parallel. Okay. And the transverse correlation correlation function is denoted by Z of R, okay. And relation in isotropic turbulence, if you find out the relation between this F and G, the relation comes as, so that relation for isotropic turbulence between these two functions is given as, sorry, that R by 2 d f of r dr. Okay. This is what is the relation, okay, for isotropic turbulence, keep it in mind. So, we understand what is f of r. F of r is defined as, okay, as I said, u I x I t u I x I plus r, this r is parallel to u I, okay. So, in this case this is essentially u I square bar, okay. And z of r, similarly you can define u I x I t u I x I r t. So, this is u I square bar. So, here in this particular case u I parallel to r, whereas in this particular case u I perpendicular to r. So, this is what is the main point to be noted here. Okay. So, that means if we now draw this correlation function in the case of isotropic turbulence, let us see what we get. So, our f of r, let us say we would like to plot the correlation function. If you plot the correlation function in the case of turbulent flow, you will see it is a symmetric function, we have already talked about. Correlation function is symmetric, right. So, this is r and this is f of r, maximum value is of course 1 normalized. Okay. So, this is what is f of r, and we know what is the definition of f of r, that already you have written there. So, definition of f of r, we can write it is a longitudinal. So, let us say we will write it as x comma t, or x no need u 1 x 1 you can write 1 you can write, and here you can write r, which is in the direction of, let us say, your this, or you can do one thing, you can do, maybe we can take a vector for most generalized case, and we can r this quantity plus r into u 1, okay. That is what we can consider, means we are going in the direction, because anyway it is independent of this function is independent of this particular quantity. So, it is only a function of r. So, we can write this as this divided by u 1 square bar, right. So, this is what is our function, and if we plot, this is what our correlation function will look like in a turbulent flow. Okay. So, now you see what we are looking for. If we would like to fit a parabola around this, then the parabola will come like this. Okay. So, what we are doing here? Nothing. We are trying to fit a parabola around this point. Okay. So, f of 0, that is what f of r is equal to 0, right. So, that means we are trying to fit a parabola, and that parabola we are trying to find what is the length of this. Okay. We will see. Now, to do that, you see, we will start with this particular quantity. Let us say f double prime of at 0. Okay. So, minus f double prime at 0, f is this and f function is this. Okay. And this one can be written as minus, by definition, limit r tends to 0 del 2 f of r del r 2. Okay. So, by definition this is what we can write. Okay. That is, we can once again write this as limit r tends to 0, and we can put the value of r here, r 2, value of r is given there. So, u 1 x u 1, let us say this is x t, u 1 this is x plus u 1 r, u 1 is a vector, sorry, it is a unit vector in the direction of x 1, t, then this is what, this one, divide what, divide your u 1 square bar. Okay. That is what we can write. Now, you see this is the only quantity which depends on r. This one is not dependent on r, this also not dependent on r. So, this quantity we can take it out. Okay. So, we can write this as 1 minus u 1 square bar, we have taken it out, and this quantity we can write as limit r tends to 0, and see this quantity does not depend on this. So, we can write this as del 2 u 1 x plus u 1 r t r 2 u 1 t bar. Okay. So, you see this particular quantity once again we can write as, see, r tends to 0. So, basically then this derivative becomes del 2 this quantity by del x 1, because we are our separation in the direction of x 1. So, this becomes then essentially x 1. That means, this quantity essentially we can write as so, this quantity if we write once again we get what, minus 1 by u 1 square bar del 2, sorry, we can write this as u 1 del 2 u 1 del x 1. Okay. This is what we get. Right. So, now if we so this is what we get. Now, you see now if we find this quantity x 1 u 1 del u 1 del x 1, this can be written as, you see so minus of this can be written as minus, minus we can write this as u 1 del 2 u 1 del x 1 2 plus your del u 1 del x 1 square. Okay. If there is a bar, we can take the bar here, take the bar here, right. So, you see what is going on. That means minus minus of this quantity is nothing but is this. That means your minus of this or U1, okay, this is fine and this is fine. So, that means this quantity is equal to this minus this, right. So, that means we need to find out minus of this. So, that means minus this is your U1 del 2 U1 del x1, okay, bar, and this is minus minus del U1 del x1 square bar, right. So, you see what do we get? So, minus of this is equal to this, that means minus of this quantity is equal to basically this minus this, right. So, that means we can write or minus U1 del 2 U1 del x1, okay, 2 equals to this quantity equals to this minus of this plus this quantity, that means del U1 del x1 square bar minus this. So, that is your del x1, okay, and you see this we can write as del half U1 square bar, okay, del x1. Okay. Now, you see we are considering homogeneous isotropic turbulence, right. So, homogeneous turbulence means the gradient does not depend, sorry, the statistics does not depend on space. So, this is from that point of view we can make it 0. So, that means this quantity minus of this. So, minus of this essentially is nothing but your this quantity. Okay. So, this is, so that means this one equals to can be written 1 by U1 square equals to what? Equals to your nothing but your this del U1 del x1 square bar. Okay. So, this is what we get. That means, so now we have got this expression is equal to this, right. So, you see here, so what is this? We would like to expand this f of r around this. So, that means what we would like to do it here? We are trying to do f of at very small r, the value is going to be f of naught plus r f prime of naught plus r square by 2 f double prime naught plus higher order term. This is from the Taylor series. Okay. So, since this correlation function is symmetric, so this is 0, f of 0, okay, f of 0 is equal to 1. So, that means this is 1 and this is your plus r square by 2 your truncating all other higher order terms. Okay. We can write expanding f of r around 0, this is what we have got. Okay. So, that means that the value of f of r, the value of f of r at some particular lambda value. What is the value of f of r? See, f of r, let us say this value is our lambda f. If this lambda f and at lambda f, that this is what? This is basically a parabola. You see, this is just nothing but a parabola. So, when you are fitting a parabola around r is equal to 0, this is what you get it. Okay. So, around r is equal to 0, if you fit a parabola, that is what you get it, and the value of f of r at r is equal to 0 here is at value of this f of lambda, sorry, it should be f of r means that is what the value. So, at the value of this quantity at this location is what? This is the axis. So, this axis value at this location is 0. Okay. So, that means this value is going to be what? This value is 0 here, and this is your r becomes then lambda f square, okay, and lambda f square or 0, that means this lambda f square by 2 f double prime 0 equals to minus 1, or f double prime of 0 or minus, you take it minus here, positive put it here. Okay. So, that means minus f double prime of 0 minus f double prime of 0 is equal to, we have got this, right. So, that means if you put that value, then what do we get? If you put that value there, then we get minus lambda, this is lambda f, sorry, lambda f square by 2 is here, 2 is here, let it be there, and f double prime of 0 is equal to, you put the value of that, u1 square bar, okay, into del u1 del x1 square bar, okay, is equal to 1. Okay. So, that is this, or from this line onward, what do we get? You see, so we have put the minus of this, so minus should not be here. Okay. So, that means you see what do we get? We get this del u1 del x1 whole square bar equals to we get u1 square bar divided by lambda f by 2. Okay. So, as I told, so this is what? So, this is nothing but your u1 square bar, this is from considering the relation of the isotropic turbulence relation, that is lambda, this is nothing but your lambda g square. Okay. So, this quantity is equal to this. So, what we started with, if you can remember that what we did. So, what do we said? For isotropic case, epsilon can be written as 15 nu del u1 del x1 square. Okay. This quantity comes from the algebra of epsilon ij bar. Okay. So, just like a bookkeeping, if you would like to have the derivation of this particular quantity, is available in the turbulence book by Hinge. Okay. So, it is available there, one can go there and check. Okay, for details derivation of this particular quantity. Now, this we wrote as u1 square bar lambda g square, u1, u2, u3 all are equal in a isotropic turbulent flow. So, this can be this where it is coming from, then it is coming from this relation is equal to this, that is what we have got it here. Okay. So, this relation is equal to this. So, what is this essentially? It is actually, so it says this particular quantity basically lambda f is this. So, Taylor microscale is nothing but it is a parabola which is fitted to this correlation function, and wherever it cuts, this parabola wherever it cuts in the r axis, that is what is your lambda f. If I would have, instead of f of r, if I would have plotted z of r, means transverse correlation function with respect to r, I would have got this as lambda z. Okay. So, that means that this lambda z is, so the definition whatever we have considered earlier Taylor microscale, this is nothing but this parabola fitted to this correlation function. Okay. Physically what does it mean? Physically, as per the as per the book by Macomb in Turbulence, this Taylor microscale or Taylor scale can be considered as the diameter of an energy containing eddy, okay, in a turbulent flow. So, that is what the definition of Taylor microscale we have got it here. Okay. So, once again I would like to mention that although we have considered that u1 square by lambda g square, or it is nothing but your you can write this as nu u r m a square by lambda g square, or this is equal to 30 nu u or u r m s square by this is it is going to be then lambda f square. Okay. So, that is what is the relation. Okay. So, means in an isotropic flow, if we know the RMS value and the Taylor microscale, we should be able to estimate the dissipation. That is what it says. Okay. And once we are able to estimate the dissipation, then we can calculate the Kolmogorov length scale, Kolmogorov velocity scale and Kolmogorov time scale. All three scale also can be estimated, which are dissipation scales. Okay. So, with this I would like to stop today. In the next class, again we start the discussion with this turbulent kinetic energy equation for some specific applications. Okay. Okay. Thank you.